Hi, this is Ken Willis from Cadence Design Systems. The next section of the webinar, I'll cover Sigrity X, redefining signal and power integrity in Sigrity 2021.1. Today's agenda will focus on some introduction, IBIS modeling updates, the hybrid solver and advanced PI updates, mainstream signal and power integrity and advanced SI updates, and also some example flows focused on DDR5 compliance and system-level power integrity. So what's the big news around Sigrity X? The big news is really distributed computing across our multi-physics analysis capabilities. So the same massively parallel architecture that was initially developed with the Clarity 3D solver has now been successfully applied to other products in our portfolio. The Clarity 3D transient solver, the Celsius thermal solver, and now all the Sigrity products that you're familiar with. But what does Sigrity X really mean to a user? What it really means is performance. So for the same trusted accuracy that you've relied on Sigrity for, you can now get that up to 10x faster. Fundamentally, what this means is coverage. That means that the detailed, computationally expensive analysis that you've in the past only been able to apply to a small portion of your design, you can now apply to a much larger portion or perhaps the entire design. It also means that you can afford to do many more iterations of analysis than you've been able to do in the past in your design cycles. That means that things like trying different stimulus patterns, process variations, manufacturing tolerances, and other aspects that you could just never get to before are now within your reach, and you can increase the coverage of the analysis in your design process. So whether your job is to put a satellite into orbit or to provide the sensors for autonomous automobiles to help keep people safe, or even to put that pacemaker in someone's chest, you can feel confident that you've provided the maximum amount of coverage you can on that design when you've gone through your sign-off process and help that design to work right the first time. People that have been in the analysis business a long time will tell you that no one's ever really finished an analysis project. They've just simulated till they've run out of time. But the feedback we've been getting from customers on Sigrity X is that we're actually helping them to finish. At MediaTek, we're told that their designs can be analyzed 10x faster with the same level of accuracy as they had before. At Renesas, they've seen the turnaround time on their simulation work shrink from days to hours. At Samsung Foundry, they've been able to deliver designs weeks earlier while maintaining the same level of accuracy for their analysis. And at H3C, they've seen that they've been able to improve quality with Sigrity X because they can afford to do more simulations, more iterations, and have more coverage while maintaining the same schedules. Next, we'll take a look at the Sigrity products that have implemented the Sigrity X architecture. We'll look at the areas of interconnect extraction, power integrity, signal integrity, and IBIS modeling. We'll review some test cases to see the impact that Sigrity X has had on performance. This first test case is for Power SI. This is for a package and PCB database merged together and uses 32 cores. This case originally ran in about 28 hours, but with the Sigrity X architecture, we saw performance improvement of about 12x, and we could finish the same extraction in about 2 hours and 19 minutes. This test case is for Power DC. And this is for a flip chip BGA package and uses 16 cores for the analysis. Originally, this took about an hour and 15 minutes. But with Sigrity X, we're down to 10 minutes and 10 seconds, which is a speed up of about 7.2x. For this info package extraction with Extract IM, we use 36 cores. This originally ran well over a week, 8 days and almost 5 hours. But with Sigrity X, we're able to do the same extraction in about a half a day, speed up of around 15x. This case was for a decoupling cap analysis with optimized PI. This again is for a PCB and package merged together into one database and uses 16 cores. Originally, this took almost 42 hours to run the analysis. But with Sigrity X, we got that down to under 5 hours. For an overall speed up of about 8.5x. Now, one of the things you worry about as an engineer when someone says that something's gone through a massive speed up is you say, okay, what shortcuts are you taking? Is it as accurate as it was before? Well, in this case, there's actually been quite a bit of correlation work done before and after Sigrity X, and you can see, looking at these plots, that the accuracy is very, very close. You're within fractions of a dB for all of these different cases, and this is very typical of what we see. So we're still solving Maxwell's equations here. We're just using many more cores and doing it with massive parallelization. If we get into the next level of detail on the speed up, you can see it can be attributed really to three main things. One is code refactoring, where we've simply improved the efficiency of some of the existing code, some new algorithms, but mostly the multi-threaded computing. Here, if you look again at the cases we've reviewed for Power SI, Power DC, Extract IM, and Optimize PI, you'll see a speed up in terms of execution time anywhere from 7 to 15x. The Sigrity X approach is also scalable. So in addition to being able to use multiple cores on your machine, you can also use multiple cores across multiple machines on your network. So just as you'd expect with a parallel architecture like this, the more cores that you can throw at these problems, the faster you'll get results. In the tables below, you can see this scalability where the execution time based on the number of cores continues to drop. System SI also directly benefits from the high-performance computing architecture. For example, if you're running sweeps and you're going to run 80 different sweeps, if you have 8 cores available to you, you can send 10 of the sweep simulations to each core and do them all in parallel. They're going to complete much faster. So in this case, you can see that we had originally a time of about 12 minutes to run the sweeps set up in this case, and we're able to do it in about 1.5 minutes for a speed up of almost 8x. The other aspect to Sigrity X besides the performance speed up is the new user interface and also some of the new features that you'll see there. Rather than have to launch each tool in its own different user interface, this has all been consolidated now into a user interface called Layout Workbench. So Layout Workbench provides the overall user interface where all the different tools like Celsius, Clarity, Power DC, etc. are simply different workflows within the same user interface. This provides a much more consistent user experience where all the common controls and menu picks are exactly the same. You also have the ability to display in either a light or a dark theme, so you can have your choice of how this gets displayed. We've also universally incorporated some of the usability feedback that we'd received. So for example, with one button click, you can toggle all panes and also reset all panes in the user interface for the Layout Workbench. Next, let's look at some of the new technology in this release. One of the new capabilities in Power SI is to create a peak value 2D distribution chart from the spatial mode simulation results. Basically, the peak value from each frequency that's swept in the 2D distribution is collected and used to build the chart. This gives the user an easy way to see how the peak values change over frequency during the extraction process. One of the new capabilities in Power SI is a new workflow for plane wave susceptibility. Essentially, you can define an incident plane wave and then plot the response of the plane to that source. Another improvement for Power SI is the enhanced support for coupling between arc traces. So arc traces have been used in RF designs for a long time, but are now being increasingly used in high-speed digital design. The ability of Power SI to handle these types of traces with the hybrid solver means that you don't have to immediately go to a more computationally expensive full wave solver to do this type of analysis. Optimize PI has implemented PDN impedance checking using a methodology introduced by Intel, Cadence, and others at the 2020 IBIS Summit. This solution is targeted towards IC and package vendors that need to set a target impedance criteria for the PCB level integrator. The component vendor supplies the MCP header and the touchstone file for the package and the IC impedance of the PDN, and also the target impedance for each of the sense locations. This target impedance allows the PCB level integrator to optimize their power distribution network to meet the requirements of the IC. In this section, we'll look at updates to our signal integrity tools. One of the key aspects of our solution is to fit into a constraint-driven flow into the Allegro front-to-back design environment. We usually look at this in terms of 3 phases. There's an exploration phase, which happens pre-design, before schematic and before physical layout, where you're looking at some of the different feasibility and trade-offs. Here we'll use the virtual prototyping and topology exploration capabilities of Aurora to explore the solution space and develop constraints to drive the physical design. And then in the verification phase, we'll use Aurora and also System SI to do full board level screening as well as detailed critical interface sign-off. Aurora's in-design analysis brings integrated analysis technology from Sigrity directly into the Allegro environment. There's dedicated workflows to perform a number of tasks there, including virtual prototyping, topology extraction, crosstalk and reflection simulation, IR drop analysis, and also impedance, coupling, and return path checking. One of the capabilities in Aurora is topology extraction. So this allows you to click on a net directly in the Allegro layout, and using Sigrity engines, we'll extract this electrical topology directly into the Topology Explorer environment. From here, you can run simulations, perform sweeps, and experiment with termination. Topology Explorer is part of the Topology Workbench platform, which also includes System SI for high-speed interface analysis, compliance kits for serial links, AMI Builder to create AMI models, and also System PI for system-level power integrity analysis. One of the capabilities that makes it easy to do upfront exploration is the trace editor. This is available in both Topology Explorer and in System SI. This gives you the ability to quickly generate W-element models for feasibility analysis, integrated with the Suite Manager to explore different characteristics, and also comes with quick templates for common categories of transmission line structures. Next, we'll look at some recent IBIS modeling updates. A number of updates were made for the IBIS 7.0 specification. One of these is the ability to include a touchstone file directly into an IBIS model. Another is support for back-channel optimization. This enables the receiver in an AMI model to take judgment on the signal quality and provide feedback to the transmitter as to how to adjust its tap settings. This was included in our AMI Builder functionality, which contains a TX and an RX wizard to help you quickly synthesize algorithmic models. The wizard will walk you through creation of an AMI model by asking you questions about the equalization. For example, whether or not you have DFE capability, the number of taps, and so forth. After entering the information, clicking the button will synthesize the AMI model for you, ready to simulate in System SI. The next section will talk about power-aware signal integrity analysis focused on a DDR5 interface. Sigrity and Clarity extraction tools can be used to populate the different blocks to make up the full system-level topology. T2B can be used to extract power-aware IBIS models from transistor-level I/O netlists. AMI Builder can be used to build the AMI models that are used for real-time adaptation of these high-speed signals. Excite PI can be used to extract the chip-level signal and power parasitics. Extract IM or Power SI can be used to perform 2.5D extractions of the package. Also, Clarity can be used to do a full wave extraction of the package. Either Power SI or Clarity can be used to extract the PCB model, again depending on whether you want to use hybrid or full wave extraction. SpeedEM can also be used to do a SPICE level extraction of the interconnect, and also can be used in an FDTD direct mode where it will use the FDTD engine directly to solve the geometries of the layout. So Sigrity and Clarity technologies provide a full suite of interconnect extraction options to populate your topologies and enable system-level analysis. The combination of advanced interconnect and device modeling together allow you to do the full system-level simulation and produce results for the DDR5 interface. Adapting channel simulation to the parallel bus problem has some significant challenges. In this case, we have million-bit simulations that need to be evaluated in order to predict bit error rate. These need to include SSN and crosstalk impact. In applying channel simulation to these types of interfaces, you have to consider how closely it correlates to traditional circuit simulation behavior, especially when you have asymmetric drivers as you do in some DDR interfaces. One of the techniques we found to work very well for this type of interface is to use a combination of rising and falling edges to characterize the channel and generate the impulse response. This tends to give a much closer correlation factor versus traditional circuit simulation. Here's a specific example of circuit versus channel simulation correlation. You can see how the results very closely align and gives you very strong confidence that you can use channel simulation to predict the performance of your high-speed DDR interface. System SI has DDR5 specific post-processing algorithms that will go through and look at the results of your simulation and compute all the metrics such as noise margin, jitter margin, and predict BER performance based on the JEDEC specification. One of the things that makes System SI very battle-hardened in the DDR area is its heavy use internally by the Cadence IP division. AMI Builder is used to create the IBIS AMI models that represent the Cadence IP. Sigrity and Clarity technologies are used to extract the interconnect for the test package and boards that are developed along with the IP. These models all come together in System SI, where simulations are performed and correlated against transistor-level Spectre simulations and first silicon. These simulation test benches and IBIS AMI models can then be provided to IP customers to facilitate the design-in of the IP. In my last section, we'll talk about what's beyond DDR5 to look at some of the advanced serial link capabilities and also some of the power integrity capabilities that we're looking at now. Escalating data rates into the 56 gig, 112 gigabit per second range and beyond push us into PAM4 signaling technology. Gray encoding, RX center sample plotting, forward error correction handling, and virtual BERT functionality all become tools in the toolbox necessary to handle PAM4 signaling. Power integrity can be looked at the system level now as well, where models extracted from Voltus, Clarity, and Sigrity technologies can all come together to build out the full end-to-end power rail. Results in both the frequency and the time domain can be reviewed to validate that your power ripple specifications are being met.
So here we see the new interface that is Sigrity X. The GUI has all been changed. It's all been updated. Notice that we are in the black theme or the dark theme. To start off, you can take this BRD file and directly translate it into this interface just by dragging it and dropping it into this window. Quickly translates it, and I'll show you just the few steps that are necessary to get from layout all the way to results. So with anything else that is Sigrity related, you just start off in this workflow pane on the left side. We've already loaded this layout file, and the next step is to check the stack up. And of course, as always stated, check all of the details here. These all come from the board database or the Allegro database directly. So all of these values should be correct and should correspond with everything that you see in the board database in the first place. Of course, you can enforce causality using a Djordjev XR method or Debye model. You can view the materials as regular. So each one of these materials, you will have different loss tangents, dielectric constants, and metals, of course, will have different conductivities and such. Now, we're not going to make any changes here. We're going to the next step, which is selecting the nets that you wish to simulate. And in this case, I'm going to disable all of the nets. Make this a little bit bigger. And we're going to turn on, do a quick search for DDR0 DQ star and hit the enter key. This selects all of those nets that start with that, with a wildcard, and I will enable the selected nets. So now we have all of the signal nets, which are accounted for. The next thing you need to do is to turn on a reference net, which is ground, and let's take a quick look at all of the geometry, minus the shapes. So what we see here is the DDR interface is fully selected, and even some of this section over here, which is just part of the same name. The ports that we're interested in are over here. So the next thing we can do is assign capacitor models if we'd like. We can assign any sort of spice model or touchstone file, anything of that sort can be assigned very easily. The spice models are not limited to just some definitions of R, L, and C. You can put any sort of passive network in any combination. The nodes can be expressed in any sort of spice that you can think of. You can also, this extraction mode is already enabled, so the next thing you need to do is generate ports. And in this case, we're just going to go quickly through this wizard to show you how easy it is to create ports. A lot of people do like to change the power net port impedance down to something low. So in this case, we'll just pick 1. And you can change this in the defaults, of course, if you want to apply it all the time in that fashion. Now, this gives me the message that it succeeded in creating ports at 7 components, and you can see them in the background there. But here's the list of all the ports, and I'll move this in just a second. And we just created 185 ports with just a few mouse clicks. Now, if you close this window, you can see that all the ports have been generated on this section here, and even that section that was off to the right. A quick little tidbit here, of course, we showed this earlier in the presentation. You can toggle all these panes so that you can get a better view of the layout and even manipulate it in this full screen form. Or if you moved some of the windows on accident, you can reset all the panes with this button and everything goes back to the defaults. Now, of course, we can set up the computer resources. In this case, I have 8 cores and 32 gigs of RAM. If this were being run on a Linux farm or a Linux server, you could do a distributed solve on a server using a queue. There are some other things coming, but in this specific case, we're running on Windows and we're going to use the local resources. So you hit OK here. You need to save this before going to anything. And the next thing you do is start the simulation. I did forget the step of setting up the simulation frequencies. You can easily just change that by going to something like 10 gigahertz, press OK. So once you start that simulation, you'll end up with results that look like this. And in this specific case, I only ran from 0 to 2 gigahertz. This is the same database, but now that I have these results, I can pass it off to Jared.
So David's created this S parameter for us, and what we want to do is we want to put this into a simple DDR5 test bench and run a simulation on a single DQ line. Again, for DDR analysis, this can be a lot more complex with more S parameters and more memory modules. Left-hand side here on their analysis options, we have our circuit simulation options. We have SPD Sim for our simulator. If you're running in the Linux environment, Spectre is always an option as well. Bus simulation here, we can set up our bus type here, our direction, whether it's a write or a read. For this particular test case, we're going to run a write. And then auto assign on whatever rank this is. Since we only have one rank, then the single rank here is selected. And then finally, channel simulation options with step responses for both rising and falling edges. You can change your time step, a delay, or even step duration here. And the bus stimulus can either be random or even. For other specific DDR options in the channel simulation, we have considered both rising and falling ramp responses. This was mentioned earlier. This provides additional accuracy in the simulations, being that rise times and fall time responses can be different. There's also some other options here for cycle and for capture or crosstalk on individual signal basis. For multi-CPU usage, you can set this here to maximum number of CPUs for the circuit simulation. In this case, particular instance, it's set to 12. Also over here, as we've been discussing about enabling distributed computing, we can set up our computer resources here. For this particular instance, we've had it set to the local host here of using a total of 8 CPUs and a total memory of 16 gig. If we wanted to try using server farm or SSH, those are also available options as well. On our analysis options down here, we have for our DQ is the only one that we're using. The rest of these options are unselected. We can set our stimulus pattern. We can use our transmit IO models here. This particular IBIS model has multiple terminations options with multiple slew options. For this one, we're choosing the 34 ohms. For the data rate, we're going to start out with 4,400 megahertz. We're going to run just a short simulation of 2,000 bits, and we're going to display 2,000 bits in our simulation results. So then after we've run the simulation, which we ran previously, we'll have our SSI viewer pop up our simulation results. On the left-hand side here, we have time domain waveforms of what your waveform looks like and various other measurements that can be made. We also have a 3D result as well, which you can either look in 3D or flatten it out to a 2D eye density plot. Down here, we also have a channel report here, reporting various statistics on the simulation that was run. But what we want to do here is, now that we have our simulation results, is we want to take a look at a report. So we're going to generate a report generation for this particular simulation. So when we right click up here, we're going to click generate report, and we have this generate report form come up. And we have various different measurements that we can do, the measurement range of where we want to start our measurements to the very end. We have different thresholds here for our DDR5s, including some LPDDR4s. So here we have 44, 52, and 6400 as our options here. We have other measurement options here. We're going to apply it just for our DQCA mask, and then we're going to generate the report. Just take a moment. So once we get our DDR measurement report, we have this HTML report that we can use for looking at all of the different setups, the DDR measurement setups, and then the results. So we're going to jump straight to the results here, and what we want to look at is, in particular, is the DQ mask report based off of the DDR JEDEC standard here of what that eye mask needs to be for this particular frequency. So clicking on this, we can pull up our eye mask here, and we see that based on the standard that we are easily passing our mask here at 4400. So what happens if we go back and we change this to 6.2, excuse me, 6.4 and run the simulation and see if the results from there, let's see how much additional bandwidth that we have on this particular circuit. Maybe we can run our memory faster. So that simulation was already previously run here, and we can look at our eye plots there and here. And here we can clearly see that the eye is definitely closed down some. So what we want to do here is we want to run the report on this particular simulation as well. So again, right click, generate report, and we're going to leave the report options the same as they were last time. So we want to check to see if we're able to run something faster on the, with the same, maybe we can run this link at a faster speed. And we want to come down to the results. And when we click here, we can see that we're actually violating the mask here. And the model report is actually generating a failure here as well. So while we may be looking for passing results, we can clearly show here that the report generator is actually catching the failures as well. Okay. Switching gears here from DDR5 to doing some power domain analysis. So we mentioned earlier in our presentation that we have this new flow that we're presenting and for power domain analysis. This is what our flow is looking like right here. We have various different building blocks from subcircuits, SMP blocks to ideal elements, and layout elements, VRMs, Voltus blocks, and then we have an IC block here. So the IC block is usually what you're going to start with here, and this is for describing what your on-die PWL and on-die power domain looks like. And in this particular instance, we can look at your PWL that you're using for simulating, and we can also describe what our IC model looks like. And we have various different options for this as well. Die model editor here, once you have your PWL pulled in here, we can actually generate and edit and modify a current profile that is provided. We can scale these, shift these, cut and paste these, merge them in both time and in current. So once you get a hold of a PWL, you want to be able to edit this and to be able to manipulate this, this is a great way to be able to do that. So once you have your IC model defined, then what we can do is we can go and generate what we want to call a target impedance. And in the background, we're using some other Sigrity X tools to be able to give us various different target impedances that we can feed back to our board and package designers. And after that is run, this is one of the example outputs that you'll get. And here we have multiple different solutions that will meet our power ripple spec that we told that we were given along with the PWL and the IC. Now, once these curves are generated, as I mentioned earlier, you can feed these back to your design teams to discuss how to have the targets met here. Once these are fed back and you start getting layouts from both your package designers and your board designers, we can start putting together a complete flow here to be able to look at impedance analysis and power ripple analysis in this particular setup. Now that we have this all together, we can look at the impedances on all 8 of these nodes, and we can compare those to the target impedances that we had. So here we actually see the target impedance of all 8 of those ports, and they're overlaid here. And as we can see, for some of the lower frequencies, we are meeting the target impedance for most of these targets, but above about 100 megahertz, we're definitely peaking out here. So this might be an indication back to the design team that we may try to reduce, we may need to reduce some of the impedance here above 100 megahertz, that this may end up not meeting to, may not be meeting our power, the power ripple spec. So once this is run, then we can go back and we can run a transient simulation. And what we'll do is we'll look at the power ripple at all of these bumps here and see if see what those look like. So once we finish that, then we can look at all 8 of these. Now, since they were all identical and all of the impedances of the network were pretty closely matched, most of these ripples are actually overlapping each other. So with this tool here, you'll be able to piece together system level power analysis and be able to do some in-depth looks at both the impedance and the power ripple results.
In conclusion, Sigrity X and Clarity 3D Solver technologies have created a sea change in signal integrity and power integrity analysis. Sigrity customers can upgrade to the new Sigrity technology for free. And if you've never used Sigrity before, contact us and we can change that. Special thanks to all our speakers today, and thank you for watching our webinar.